Beginning with C++11, the auto keyword was repurposed to provide type inference. We've seen how this works in the chapter on data types. Here I have a working copy of decltype.cpp from chapter 8 of the exercise files. And you notice at the top here we have a number of variable definitions. We've got an integer, a C string, and a string object, the standard library string type. And here I use the auto keyword to declare a variable x of the string type, and something called decltype, which we'll get to in a minute. And now when I build and run, you see it reports the type ID name of each of these. And this is very implementation dependent. So most of these will probably look different on different compilers and different operating systems, and that's okay. The type ID is really meant to be compared, not to have the name used. But here we're using the name just to show you that they're different. And so the integer pointer to constant character, so that's this constant character string. And then this string type has this long name, which is sometimes called basic string. And so those are the types of the different objects. Now you notice that X is also a string. It's the same as string object. And you notice that Y is also a C++ string class. And this is how it's declared with this decltype. So this is new also in C++11. The decltype keyword provides a type declaration based on the type of an expression. So in this case, the expression is X, which we know is a string type. And so whatever that expression returns becomes the type that can then be applied to a new object. In this case, we're just declaring a simple object called Y, and you see that the type of Y is exactly the same as the type of X. Okay, so that looks cool, but what's it really useful for? And this is where we get to something really cool. So I'm going to create a template function here. So here we have a template function, and there's a couple of things here that you haven't seen before. So the template keyword followed by the template argument list, which defines two types in this case, a left-hand side type and a right-hand side type. So it's allowing both of these arguments, left-hand side and right-hand side, to be of different types. And the return type needs to be derived from whatever the result is when these two types are added together. So in the case of most objects or most class types, this plus sign will be overloaded and it will work in different ways depending on which arguments are which. And so in a normal template definition, there would be no way for the compiler to know what this return type is by the time it gets to that keyword auto. And so that's what decltype is for. So you see this dash right angle bracket, and that's after the normal function signature. And so that's called a trailing return type. This is also new in C++11. It's necessary because of how templates are parsed. When the compiler encounters the normal leading return type, in this case the auto keyword, it doesn't yet have enough information to determine what that type may be. In this case, it hasn't even seen the left-hand side and right-hand side parameters, so it doesn't know what type they are. And even if it knew what type they were, it wouldn't know what type to return because it doesn't know what's going to happen in the function. And so this is where decltype comes in. We take decltype and we pass it an expression, and it already knows what these types are because the compiler compiles in order. And this gives it an opportunity to gather that sufficient information to derive the return type without having to make a second pass over the function signature, which actually is quite expensive for a compiler to do in terms of processing time and resources. And so with the trailing return type, it now has enough of that information. It can use decltype and an expression to derive the return type, and then whatever goes in auto, which is really just a placeholder here, can then be determined. So let's see this in action because this is actually pretty cool. This is something that you couldn't do before C++11, and this may not actually work on some compilers. A lot of compilers are still implementing, as I record this, are still implementing all of these features from C++11. So I'm going to declare a variable here, and I'm going to give it auto type and call it Z, and it'll be the return type of TF. Now, I'm not using a template argument list here to give it the types. I'm letting it infer them. Normally, I've said this before, I would always use a template parameter list, but in this case, I want it to infer them just to demonstrate how this works. So I'm going to give it our C string and our string object. And then we'll see what the type is. So type of Z, and we'll also give the value here. So cout Z is Z. And when I build and run, you see that Z is the concatenation of those two strings. This is a C string and this is a string class string. So those are concatenated without any space in between. And the type is the basic string class. So that's the C++ standard library string class. Now, even though these two arguments are of different types, what it did is it took this expression of the C string plus the string class, and it operated on it with the overloaded operator to see what that type is, and it derived that type and set the return type as a string class. So even if I turn these arguments around, it still works and we still get that same result. So that's what decal type is really used for. Most often you'll just see it used in a trailing return type in a template function. So the decal type keyword allows type inference for template function return types. This is essential for generic programming, and it's actually used quite a bit in the standard template library.